Okay, welcome back to Lecture 8 of Quantum Computer Systems. Today we're going to move on to the third module of the course, where we study noisy quantum systems. And in particular, this lecture will be focusing on how we should adapt quantum algorithms to these noisy characteristics. And the next lecture, we're going to talk about questions like, what are those noises look like? And what are their impact on computation? And finally, in the third lecture of this module, we're going to look at compiler optimizations in the presence of those noises. So for this lecture, first we're going to motivate why we need to adjust our algorithms for the NISQ era, and then talk about this hybrid quantum classical information processing framework using the example of variational quantum eigensolver. And then we're going to distill the component of this new framework down to its components, its key components, such as quantum objective function and parameterized quantum circuits. During the process, we're going to see, now as we understood, there are a wide range of applications using this hybrid quantum classical processing model, including quantum chemistry, combinatorial optimizations, and if we have time at the very end, we will hint at its potential applications in machine learning tasks. Okay, let's get started. So as we have seen in the first two modules of the course, implementation of quantum algorithms can be very expensive. We know they can cost many number of qubits, also known as quantum algorithm with a large quantum memory footprint. An algorithm can also take many gates to complete, therefore with long computation time. We also know the system software can be really complex if we want to run large quantum algorithms. And finally, and more importantly for this module of the course, we're going to talk about how the hardware limitations will impact or inspire the design of quantum algorithms. On the bottom right of this slide, I'm showing the resource requirements of many existing quantum algorithms in terms of how many number of qubits it needs and how accurate gates needs to be in order to run these algorithms successfully. We are seeing devices getting larger and larger and more accurate over the years, but there's still a substantial resource gap that prevents us from executing those large algorithms directly on these existing hardware. And the reason that these emerging devices are challenging to scale up is largely because the level of quantum noise in these devices are relatively high. But don't forget, we have these powerful classical computers at hand. Can we think of a way to solve a problem using both the classical compute resource as well as the quantum compute resource? And maybe because we integrate them very well, every time we use the quantum resource, they don't exceed their current capability. And that is precisely what we are going to do in this lecture. We're going to propose a hybrid algorithm that combines the quantum compute resource as well as classical compute resource. And remember, when we use these quantum resource, we have to be aware that we might only be able to afford a small number of qubits and very shallow quantum circuits. Now let's think about how do we integrate the quantum computer and the classical computer. Well, one naive way of doing that is that you let the two take turns. First, you run a small quantum circuit. And second, you use the results from the quantum circuit to perform some optimization on a classical computer. And then you run your second quantum circuit and perform some classical optimization using the result from the new quantum circuit, and so on and so forth. Now you can interleave the classical processing with the quantum processing with the hope that with more and more iterations, your answers gets better and better. The high-level idea can be summarized as this guess and check methodology, where a classical computer take a guess of some parameters, and the quantum computer will check if the guess is indeed a good one. And hopefully the quantum computer will also inform the classical computer what a better guess would look like. Now let's take a look at one example computational task that will be amenable to this guess and check methodology. This is called the variational quantum eigensolver. And the problem here is that you want to compute the lowest eigenvalue of some matrix H. And when I say the lowest eigenvalue, I mean the smallest number E0 that satisfy this equation. H times the eigenvector E0 is equal to the eigenvalue E0 times the eigenvector. Now, the first question we want to ask ourselves is, why do we need a quantum computer to solve that? Well, it's because I'm going to make this problem harder by making this matrix H very, very large. For example, with size 2 to the n times 2 to the n. Then the cost of finding the lowest eigenvalue with a classical algorithm will also be exponential in n. But it turns out that this guess and check strategy works very well for this particular problem. Okay, now here's the proposal. First, we guess a vector, and then we check if it's close to the eigenvector E sub 0 associated with the lowest eigenvalue. Okay, now how do we use a classical computer to guess? We can parameterize the quantum state vector with some classical parameter, call them theta. Okay, so those are some free classical variables. Or alternatively, you can think of it as a quantum state prepared by a parameterized quantum circuit. To write them as U theta acting on your initial quantum state, say it's all 0. That's a guess from the classical computer of those theta parameters. And then we use the quantum computer to check. Now let's see if a quantum computer can give us information about whether that vector we just guessed is close to the eigenvector E0. It turns out that if you can think of the matrix H as an observable, so a measurement rule, remember from our first module of the course, then measuring the observable H on the quantum state psi can be written as in this form. And let's say the measurement result is denoted as C sub H of theta. The assumption is that the matrix H is a Hermitian matrix. And again, the definition of Hermitian matrix is that the matrix itself is equal to its conjugate transpose. With this assumption, now we can view the matrix H as a measurement using that observable on a quantum computer. Now, how does this help us find the lowest eigenvalue of the matrix H? Well, we have this really nice variational principle that states for Hermitian matrix H, in any vector psi will always have psi H psi larger than or equal to the lowest eigenvalue of H, E sub 0. Now, assume this is the case, we can define our objective of this guess and check procedure, that we want to find the set of parameter theta that minimizes the number C sub H of theta. So we can just keep trying different vectors psi of theta, and the goal here is to find the global minimum in the theta parameter space. Now, the proof of this variational principle is in fact very straightforward. For the interest of time, I'm going to leave that as an exercise, but the hint I can give you is that for a Hermitian matrix H, its eigenvectors form a orthonormal basis. Okay, now let's summarize again how to compute the lowest eigenvalue with this variational approach. On one hand, we have the quantum routine, where we start with 0 quantum state, goes through a quantum circuit that's parameterized by some variable theta. At the end of this quantum circuit, we have prepared a quantum state psi as a function of theta. And the problem we want to solve here is a objective function obtained via measurements. And this is a special measurement of the observable H. So I'm going to label this measurement with the H, the matrix in the problem. And the measurement result is written in this form. Okay, so we are going to pass this measurement result into a classical optimizer. So this is the classical routine. And the optimizer is going to inform the quantum process of what parameter to use next. Now, overall, the objective is to find the parameter theta that minimizes this objective function. It turns out that this hybrid quantum and classical routine is very useful in the context of quantum chemistry, where in that case, the matrix H is the so-called Hamiltonian of some electronic structure or molecule, and the lowest eigenvalue correspond to the ground state energy of this molecule. So we can use this hybrid quantum classical algorithm to find the ground state energy of some molecule. Now, up to this point, you should have a rough idea of how this hybrid algorithm and the classical quantum routine should work. But really, there are many potential issues with this algorithm. For example, I haven't explained what is a good initial guess for the parameters to be used in the first round of the quantum circuit. And what is a good parameterized quantum circuit for a particular problem? And how do we implement this objective function that wrote psi theta h psi theta? How do we implement this observable H? Also, what is a good optimizer to be used on a classical computer for this task? And finally, how do we guarantee that this algorithm will converge or has a termination condition? And above all of that, why do we use this quantum classical hybrid model to solve a computational problem? Do we have an advantage of doing so? All of these problems are being actively explored in the community right now. And I just want to share a few remarks about some of those questions. Now, when we get a classical computational problem, such as an optimization problem, shown on the top right. Here we have a classical objective function, C sub p is a function of input theta. We want to find the set of parameter theta that maximizes or minimizes the cost function C sub p. Now, given this computational problem, well, the first question is whether we want to use a quantum computer to solve this problem. Well, if the answer is yes, it's typically because of two things. First is that the cost function p c sub p is expensive to compute. And in many cases, there are too many parameter theta to try to find the maximum or the minimum. But on a quantum computer, you could potentially encode all the inputs in qubits so that you can try multiple parameters theta at the same time with the superposition of the quantum state. And hopefully you can also construct a quantum circuit that obtain the output of the cost function very efficiently. For example, through quantum circuit plus measurement. But to make this hybrid algorithm work, we really need to define very carefully each of these steps. involved in this process. We want to define an observable matrix H associated with the problem P so that the cost function C sub P can be obtained by measuring this observable on some quantum state psi. Now the questions become, what is this observable? How do we implement it on a quantum computer? And what is this parameterized quantum state? And what is its implementation? Now, a simple example of such a problem observable is, say, a linear function of a set of measurements. So what we can write is that the matrix H is a linear combination of multiple measurement O sub I. The Wi is the coefficient associated with that measurement. With this definition, the cost function can be computed by a set of measurements, namely measuring O sub I on the quantum state psi, and do that multiple times for each O sub I. Now, each O sub I could be as simple as a measurement rule, such as a Z basis measurement on qubit 1, X basis measurement on qubit 2, etc. But the goal here is that through that set of measurement, we can compute the value of our cost function C sub P. Now, how do we implement the parameterized quantum state? It's prepared by some quantum circuit use of this data on the initial state, for example, the 0 state, where the quantum gates in U of theta are parameterized or conditioned on parameter theta. For example, in the quantum circuit, you could have a series of rotations, and the angles are the parameters theta. Or depending on the parameter theta, you can decide on forming a quantum gate X or not performing the quantum gates. And last but not least, if we want this hybrid algorithm to work, we need to make sure that with more and more iterations of this hybrid quantum and classical routines, our answers will get better and better. So the guesses from the classical computer should really be very well informed. For example, if we know the gradient of the cost function in terms of the parameter, then the optimizer are able to provide a next set of parameters in a gradient descent search style. And such gradient may be obtained with parameter shift strategy, where you incrementally move the parameters in each direction and find the direction that suits you best. Or sometimes you can directly measure the gradient of the cost function as a function of the parameter theta, in which case you can form such measurement to help the optimizer. Now, if you have answers to this sequence of questions for a particular problem, then we have just designed a new hybrid algorithm for that problem. And we're going to illustrate that with one last example called the quantum approximate optimization algorithm, also known as QAOA, in just a single slide. So in this problem, we have an optimization problem called the max cut of a graph G. The goal of this problem is to find a cut of the graph. In other words, we partition the vertices of the graph into two sets so that you can draw a line across the graph so that all vertices in one partition are on one side of the cut and all vertices in the other partitions are on the other side. For example, in this example graph that I drew on the left-hand side, we have a 5 vertices graph, and the cut that I drew here is in the red dashed line where vertex 1, 3, 5 are on the left side of the cut and 2 and 4 on the right-hand side of the cut. And the objective is to find a cut such that the sum of the weights along the edges that the cut crosses is the maximum. So in this example, the cut crosses 4 edges so that the sum of these weights are the maximum among all valid cuts of the graph. And the way to solve this problem is to find a good partition for the vertices. For example, we can assign a variable z for each of the vertices. For example, vertex 1, 3, and 5, we assign +1 for the variable, and for vertices 2 and 4, we assign -1. Mathematically, the objective can be written as a function of the assignment z for each vertex. And what the objective function calculates is the sum of the weights associated with that particular assignment, that is the particular cut. For example, you can verify that if for one of the edges I, j, zi is +1 and zj is -1, then this term contributes wij to the summation. Whereas if you have +1 on both variables, then this term cancels out to 0. So you are only summing over the weights of the edges that cut across two partitions. Now let's answer the sequence of questions that can lead to a hybrid algorithm for this particular problem. First, why do we want to use a quantum algorithm? Well, in order to find the parameter z that maximizes the objective function, you can see that there are too many choices of z to consider. In particular, there are 2 to the n possible choices for the input z. And to compute the cost function c sub g, we need to sum over all the edges, which could be very expensive for large or dense graphs. Maybe we can encode the input z into qubits and use superposition of quantum states to try all the possible assignments at the same time and potentially give an advantage in computation time. So let's continue the list of questions to see if we can make it work. The quantum objective function that we want to calculate in this case maps the classical objective function to a quantum version so that the cost function no longer takes in a classical binary string, but rather it takes in qubits. So quantum state, as we discussed, this can be some parameterized quantum state that we don't know its parameter yet. And ideally, the measurement outcome of the quantum state psi on a problem observable h sub g will give you this cost function. Now let's see how can we define this problem observable that calculates the sum of the weights of edges that crosses the cut. And in fact, we can do that by writing something very similar to our classical objective function. So the observable matrix will be sum over edges ij, the weights wij on the identity matrix minus the poly z matrix on index I, tensor with poly z matrix on index j. Okay, so the reason we want to do that is that if you measure observable z on 0 state, you get +1, and measure observable z on qubit 1, you get -1. So this is just like our classical zi plus and -1 assignment. In other words, what we're doing here is that we assign a qubit for each vertex of the graph. In the blue partition or the +1 partition, we assign 0 quantum state. And for all the green vertices or -1 vertices, we assign 1 for the qubits. So at the end of the day, this assignment becomes a quantum state psi that has 0 on the first, third, and fifth indices, and 1 at the second and the fourth indices. So if the quantum state psi is 0, 1, 0, 1, 0, then equivalently the measurement outcome from the observable Hg on this quantum state psi is equal to our classical objective function on the string plus minus plus minus plus, which is the maximum that we wanted, as we found earlier here. Now we have a clearer picture here. We want to use this quantum algorithm that can calculate the objective function and that can guess this quantum state psi. Such a parameterized quantum circuit that I'm going to write down here is called the QAOA ansat. It has a simple description. It's an iterative quantum circuit. We start with a uniform guess of all possible quantum state, and that is the all plus state. The first set of quantum gates that you want to apply to this quantum state is what we call the problem layer, denoted as U sub G gamma, where gamma is the variable or parameter of this layer. And I'll explain what the unitary gate is. Second set of quantum gates that we want to apply here is Rx rotation on all qubits. And this is what we call the mixing layer. Depends on parameter beta. And we want to repeat this p times until we perform the measurement of the observable h sub g to obtain this cost function. The definition of this u sub g is pretty simple, namely e to the I gamma h sub g. And this can be implemented by applying RZ rotation of gamma angles on appropriate qubits. And these qubits are specified in our problem observables, namely qubit I and j for each of the terms. So why this parameterized quantum circuit? Well, in fact, this quantum circuit, this iterative process of two layers, is inspired by this quantum adiabatic algorithms. And it has really nice properties or performance guarantees. To name a few, for example, well, the performance of this quantum circuit, the ability of it to find the best quantum state psi that maximizes the cost function, depends on the graph structure, how large the graph is and how densely the edges are in the graph, as well as the number of repetitions of these two layers, p. So the performance depends on the graph G and the parameter p. The nice thing about this quantum circuit is that even for p equals 1, so just no repetition, one can prove a guaranteed minimum approximation ratio. In other words, you can get at least some factor of the true maximum value of the cost function using this algorithm. And furthermore, this approximation ratio can only improve with increasing p. When p goes to infinity, so a deep quantum circuit, one can show that the approximation ratio approaches 1. The behavior of this quantum algorithm in other values of p is not so well understood, and it's still being actively explored in research. But this is just a demonstration of how useful this framework of hybrid classical quantum algorithm can be in solving various problems, including the scenario where you have a physical problem like a molecule and you want to find its ground state energy. That can be reduced as a problem of finding the lowest eigenvalue of a Hamiltonian matrix, or it can be some combinatorial optimization algorithm, such as the max cut problem in this case, all with really nice performance guarantees. But the true application of this hybrid classical quantum algorithm relies on the discovery of more problems that's suitable for this and a successful implementation of this algorithm on a real hardware. So next lecture, we're going to study what are those quantum noises that we have to be aware of when we design quantum algorithms or design the system software for running these algorithms.